Okay, recall that two samples are said to be independent if the selection of one group has no effect on the selection of the other group. Well, today, when we're dealing with paired data, we're getting rid of independence, because paired data is not independent. And that's okay, because the reason for our pairing is because the pairs they're matched in some meaningful way that is going to make our experiment or our outcome be more valuable for us. So in a lot of cases, it says using independent samples is not the best way to investigate a difference between two populations or two treatments. So, I mean, if you think of, like products we use on our bodies, okay, like we use, skincare stuff or shampoo, it's like acne solutions, hair growth stuff. A lot of times it's best if you pair people that have similar situations or similar skin problems or similar types of hair, and you pair them up, one to use like the old and one to use the new product. You can also pair someone up with themselves. So maybe they want to test whether a certain type of acne lotion works. So they might have you, try the old type for a while and then wait and then try the new type, or do one on each half of your face. And that is a very effective way to test things, but it takes away the independence. Okay, it takes away independence. But that's fine. We can still use it to prove things. So, for example, in our experiment to determine if caffeine affects pulse rate, we could have assigned the treatments completely at random, but since other factors affected pulse rate, such as gender, resting pulse rate, the variability in pulse rates caused by the caffeine may be obscured by the variability created by other factors. That was a lot of words just to say that our caffeine experiment was not that great, okay? And that's fine, that's perfectly fine. Some experiments don't go as planned, okay? We should have maybe paired people up who had similar resting heart rates and then gave that one caffeine and one not. That would have been a good study to do data pairing, okay? To even out the effects of these other factors, we didn't pair the subjects, but we could have paired the subjects by gender and initial pulse rate. So then when we analyze the results, we look at the difference in each pair. So what we did when we had means of two samples before is we found the mean of each sample first. So in the previous lesson, we found the mean of each sample first, and then we subtracted them. But what we're going to do here today is we are going to subtract first. So if we're going down to the bottom of the paper here, we will subtract and find the difference first. So we're going to find the difference between two treatments first, and then we really end up with one set of data. So we do the subtraction or the difference first this time, and so this is called a matched pairs t-test. It is exactly like a one sample t-test, because we do the difference first and then we find the average difference. So that's the difference between a matched pairs, because we purposely paired up our data before we started, and we're going to do the subtraction first. So paired data occurs in many ways, especially in experiments. So measurements on a single individual before and after treatment. So that could be person being paired with itself. Measurements of two individuals who are paired based on some similar characteristic that might otherwise confound the results. They're blocks of size 2. That's what matched pairs are. Measurements of naturally occurring pairs, twins, right hand, left hand. So paired data can also occur in observational studies. Measurements at two different locations in a river to measure, say, pollution levels. And measurements of husbands and wives, measurements on the inside and outside of a house, like temperatures. You want to see how your insulation is working, if it's working evenly throughout your house. So you would go find the temperature outside your house in various locations, and then inside your house at the locations that are close, at a window. So you'd measure the temperature outside the window and inside the window. Outside a wall and inside a wall. Are your windows insulating like they should be? So, paired samples often provide more information than independent samples because extraneous variables are screened out. You get rid of a lot of those things that cause differences. So in other words, if the observations are paired in a meaningful way, a paired design will have more power. It'll have more power than two independent samples. So the fact that we don't have independence is not a big deal. Okay? We have more power because we've matched these pairs in a meaningful way. So we're going to look at a situation here to compare two SAT schools, A and B. Okay, basically it'd be like going to, we used to offer the ACT prep class here, and then somebody at Briarcliff or Morningside offers one at night. It'd be like sending some students to, sending students to one school and the other, and then comparing how they do on the ACT. So we've just got two different schools, A and B, and they prepare students to take the SAT. 14 subjects were recruited and paired by PSAT score. So they asked for volunteers, and then they looked at their PSAT scores, and they said, okay, well, you had very similar PSAT scores. One of you is going to go to school A, the other is going to go to school B. But they were paired because of their PSAT scores. And then they were going to pair them up after they took the class, after they took the SAT, and then compare their scores. So one person from each pair was randomly assigned to go to school A, and the other was assigned to school B. After 3 months, they all took the same SAT test, and their results are below. Is there a significant difference between the schools? So what we're going to do now, the difference, what we would have done last time if we were going to do a two-sample, okay, if you're going to do a two-sample t-test, here's what you would do. You would find the mean. You would find the mean of each sample, then subtract the means. So you'd find X bar of sample 1 and X bar of sample 2, and then you'd subtract them. Okay, that's what you do in a two-sample t-test. But what we are going to do today in a matched pairs t-test is we are going to subtract the data for each pair and then find the mean difference. So we're going to subtract the data for each pair and then find the mean difference. So you'll just be finding one mean, the mean difference, or X bar of the difference, rather than having two X bars that you're going to subtract. So what we're going to do is we're going to take the difference, and our difference is always going to be the same, A minus B. So if I just subtract A minus B, I get 10 and 30 and 40, 40, 10, negative 20, and 50. So those are the differences. I just subtracted school A minus school B. Now I'm going to add these up. Now I'm going to find the mean difference. Okay? I'm going to take the difference column and find the mean difference. So I'm going to add all of those values up and divide by 7. 22 point what? 9. So the mean difference is 22.9. And we probably are also going to need the standard deviation, so it's probably just best, you don't want to calculate standard deviation by hand, do you? Okay, so somebody, yep, just enter them in a list. So the standard deviation of the difference is 24.3 and n is 7. All right, so we have our data here. What would be our null hypothesis? So the null hypothesis here would be that the mean difference is equal to 0. Okay, you're not even a matched pairs test is a difference of two samples, but it's not in your null. It's the mean difference, okay? The mean difference between these two schools is 0. What does that actually mean as far as? Both schools prepared the students equally as well. All right, the alternative hypothesis is that the mean difference is not equal to 0. This would be a two-sided test because they're not saying, well, is school A better? They're just saying, are they different? So it's a two-sided test. Okay, not all matched pairs tests are two-sided. You could have asked the question, is school A better? Okay, and then it would have been, is the mean difference greater than 0 because we subtracted A minus B? If it asked the question, is school B better? Then the alternative would be the mean difference is less than 0 because B was the second one. All right, so let's go on to the next page. And guess what? We have the test all here, all 5 steps are already done for us. So the 5 steps. For this test, we're analyzing the differences in each pair, not the individual observations. So a matched pairs t-test is really a special case of the one sample t-test. So it's like we're just doing a one sample t-test here. So at first glance, it seems that the true mean difference in SAT scores at the two schools is not 0. And we say that because the mean difference is 22.9. Okay? It seems like at one school is better because the difference is 22.9 points on the SAT. Not that that's a huge amount, but okay. However, it is possible that the schools are in reality equally effective and that we got a sample mean difference this large due to randomization variability. And that's because it's an experiment. We assigned them. Okay, to decide, I will conduct a matched pairs t-test for the mean difference, and alpha is 0.05. Again, you can pick alpha. You could pick a 1 if you want to every time. All right, so our null and alternative hypotheses are here. The conditions, all we have to check is that they were randomly assigned. Yes, they were randomly assigned to the schools once we paired them up. And the population of differences is approximately normal. This is the normal probability plot again. You'd enter those differences in a list and then you do your stat plot. This is exactly the same. This is what you get. It's what it looks like. Okay? They are roughly linear. If I draw a line, they're all pretty close to that line. So that means that I can use a normal, approximately normal, and I can use my test statistic. Now this, we're going to have to do some writing here. We haven't calculated the p-value.
So for this one, we just have to check randomization and normality.
Okay, no, not this test because it was an experiment.
Experiments, you only do that.
Experiments.
If it's a sample, then you do independence as well.
Yes. If it's like a survey or observational study, then you have to check to see if it's less than 10% of the population. And it mentions that here in the note right there. It says for surveys we need to check different conditions for independence. So, and it does say that pretty much every time in the notes. So if you read it, you'll eventually get it stuck in your head. All right, so our test statistic is calculated D, the mean difference. This is our observed difference minus our hypothesized difference divided by the standard deviation over the square root of n. And degrees of freedom are n minus 1. So what is my mean difference? X bar of the difference. 22.9. What is my hypothesized difference?
Zero?
It's 0, yes. That's the value. The hypothesized value is the number in the null and alternative hypotheses. It's 0. And then my standard deviation from the previous page was 24.3. And how many degrees of freedom would I have? 6. N minus 1, yep. Okay, so I'm finding the probability that the mean difference, X bar of the difference, is, well, okay, not equal to 22.9. Okay, so yeah, I'm going to have to pick one less than or greater than. So we need to pick what makes most sense for our sample. This is where you look at the sample. Which one appears to be better?
A.
A. So we would want to go the greater than